video is about the norm and unit vectors. We've already discussed the norm a little bit. When you first were introduced to vectors, you found out that a vector is a quantity that has a magnitude and a direction. So the norm is another way of saying the magnitude. So the norm is a positive scalar quantity. It's not a vector, it's the magnitude of the vector. It'll have the units of whatever the vector represents. So in this case, let's say vector A, as I've drawn it below, has a norm of 500 newtons. A must be a force vector if it has units of newtons. When you see this symbol that means the norm, it looks like absolute value bars. But if there's a vector inside of those absolute value bars, you shouldn't say absolute value, you should say the norm. So the norm of vector A is 500 newtons. In vector space, the norm of a vector, it means the length of the vector. Remember that we draw these arrows, and the length of the arrows tell you about the magnitude of the vector. So if I add these two new vectors, B and C, notice that their lengths are smaller than vector A. The lengths of vectors B and C are the same, so they must have the same norm. So in this case, vectors B and C have a norm of 200 newtons. And you can tell that their lengths are approximately 2.5 times as small as vector A. Another way of showing this is using a grid. So I highly advise you to get some graph paper. You can buy it or you can download it from a free website. And so when you're doing your homework and when you're doing your exam, it'll help you to keep things to scale. It's really important to draw your vectors to scale so that you can keep track of the lengths of everything, because it's very important. So in this particular grid that I've drawn in this slide, every side of the square on the grid represents 0.5 meters per second. So the vectors that are on this grid are velocity vectors, if they have units of meters per second. And I want to figure out the norm of each of these vectors. So let's use the grid to our advantage to kind of count the squares and figure out the norm of these vectors. So I see vector R pointing to the left, and it goes through 4 squares. So it starts over here, it ends over here. So the norm of vector R, I write vector R and I put the absolute value bars around it. That means the norm of vector R is equal to 4 squares. And there's a conversion rate that 1 square is equal to 0.5 meters per second. So don't forget unit conversion. I taught you that for a reason. The norm of vector R is now, I can calculate it as 2 meters per second. So 4 squares, each of them is 0.5 meters per second. So now I get that the norm of vector R, 2 meters per second. Let's try to do vector S. It's a little bit tougher because it's pointing down at an angle. So vector S points down 4 squares, and it points to the left 6 squares. So let's do that other unit conversion. Let's figure out how many squares or how many meters per second this is. So 4 squares, where every 1 square is 0.5 meters per second. That means that it's pointing down with 2 meters per second. It's pointing to the left at 3 meters per second. So I'm going to redraw this triangle in units of meters per second. So here I have my vector S, and I'm going to form a triangle here where the vertical side of the triangle is 2 meters per second, and the horizontal side of the triangle is 3 meters per second. So if I want to find the length of vector S, do you guys agree with me that vector S is just the hypotenuse of this triangle? So I could use Pythagorean theorem, and I could get that the length of vector S, or the norm of vector S, is just the square root of 2 meters per second all squared plus 3 meters per second squared. And so if you do that calculation, you should get 3.61 meters per second. So that's the norm of vector S using our grid, counting squares using geometry. That's another way of finding these vectors if they are represented only in 2 dimensions. Another definition I want you to remember and just have ready to use in just a few more lectures is that the norm of a vector is defined as the square root of that vector dotted with itself. We mentioned this form of vector multiplication. It's called the dot product. It results in a scalar. And so the norm of a vector is the square root of that vector dotted with itself. Just remember that. We'll use that in a few more classes to come. The next topic is unit vectors. These are special vectors that have a norm of 1. So that's what makes them special. We give them a special symbol to make sure that we differentiate them from regular vectors. The unit vector is given a symbol that has, it looks like a little hat. So like unit vector A has this hat on top of it. So sometimes I'll say unit vector A, sometimes I'll say a hat. And so those phrases should signify in your brain that this is a unit vector and it has a norm of 1 unit. So it doesn't have any units involved with it. The norm of a unit vector is literally the number 1, no units allowed. So in this example here, I have a bunch of unit vectors drawn for you. Notice that the directions of the unit vectors can be anything. The thing that makes them special is that their lengths or their magnitudes or their norms are all equal to the number 1. So all these unit vectors that I drew for you, they all have the same length. I made sure to draw them so that they all have the same length regardless of the direction that they're pointing in. And these unit vectors, we typically use them to set the scale in a problem. So if a unit vector has a length of 1, that tells you what a distance looks like. The number 1 sets the scale, and you can use it to define all the other vectors in the problem. So let's try to do that. If we're given a unit vector, let's try to use it to construct some new vectors. We'll start off with a simple example where vector m is defined as negative 0.25 times unit vector b. So let's say you know unit vector b. It's pointing to the left and it has that length as I've drawn it. I can now express vector m because I know what vector b looks like, b hat looks like. So it's negative 0.25 times b hat. So the negative tells us that it should point in the opposite direction as b hat. And the 0.25 tells us that it should be 0.25 times the length of b hat. 0.25 is the same as a quarter. So maybe that'll help you kind of do this a little bit faster, that vector m is a quarter as long as vector b, and it points in the opposite direction. So vector m looks something like this. It's 1/4 the length of b hat, and it's in the opposite direction because of that negative sign, opposite direction. That one was kind of easy because it was, just a one-dimensional vector. Let's try to do this in 2 dimensions. Let's say that vector n is actually the sum of 2 other vectors, 3 times b hat and negative 2 times c hat. I challenge you to pause the video right now and try to do this on your own. See if you remember the rules of vector addition. I'll give you vectors b hat and c hat. You definitely need to know those in order to do this problem. So let's say you're given b hat and c hat. I challenge you to pause the video right now and see if you can draw vector n based on these unit vectors. I'm going to go ahead and do it. First, I'm going to find 3 times b hat. Then I'm going to find negative 2 times c hat. I'm going to place those vectors tip to tail, and then I'm going to draw the resultant. Those are the steps of vector addition. So let's first find 3b hat. I'm going to start right here. Notice that vector b hat, unit vector b, is pointing to the left 3 squares. So 3 times that is going to be 9 squares. So this is 3 times b hat. And now I'm going to add to that negative 2 times c hat. So c hat points down 3 squares. And so negative 2 times that points up 6 squares. Okay, so those are my 2 vectors I wanted to add together. That's why I've placed them tip to tail. And now I'm going to find the resultant. The resultant starts at the tail of the first one and points to the tip of the last one. So that is my resultant. That is vector n. So vector n is pointing up and to the left, and you can count the squares. It points to the left 9 and it points up 6. And so that's how I know what vector n looks like. You should check your work and make sure that you have the same length and same direction as my vector n. Another use of a unit vector is to help separate the magnitude and the direction of a regular vector. So we can use a unit vector to describe the direction of a vector, and then use the norm of that vector to describe the magnitude of that vector. So in this case, let's say that we know unit vector b hat. And we want to construct vector b. Notice that these vectors have the same name. That's on purpose. So vector b, this is a definition here. Vector b is defined as magnitude of vector b times unit vector b. So notice that the magnitude of vector b, that's the magnitude or the norm, and unit vector b, that defines the direction. Remember, a vector is defined by its magnitude and its direction. So I can kind of separate those two quantities and describe them in different ways and put them together to describe the entire actual vector b. So if I want to construct actual vector b, I need to know the norm of vector b. So let's say in this example, vector b has a norm of 5 meters. And I know unit vector b. That means that vector b is going to point in the same direction as unit vector b, and it's going to have a length that is 5 times as big as unit vector b. So knowing this information, I can draw vector b. Points in the same direction as unit vector b, 5 times as big. So this is one use of a unit vector, is to describe just the direction of that vector. Maybe I don't really care about the length of vector b. I just needed to know the direction of it. Unit vector b holds all of that information. We can also go in the reverse. So let's say we know a vector and we want to create a unit vector to describe that direction. What we can do is we're going to create a unit vector. It's going to have the same name as our original vector, and it will describe the direction of that vector. So in this example, I know vector b looks something like that. It's really long. It's pointing up and to the right. I know the length of this vector. Now I need to define a unit vector that just describes the direction of this vector. So if the definition of vector b says that vector b is the norm of vector b times unit vector b, that's a definition. If I just divide both sides of this equation by the norm of vector b, I can get the unit vector all by itself. So did I break any rules here? I remember I told you that we're never allowed to divide by a vector. Did I accidentally divide by a vector? No. Remember that the norm is a scalar. I didn't break any rules. You're allowed to divide by a norm because it's just a scalar. That's just a regular old number. So unit vector b is 1 divided by the norm of vector b times vector b. If you do this, let's say, for example, this vector that I've drawn has a norm of 6 meters. That means that unit vector b is just 1 divided by 6 meters times vector b. It's telling us that unit vector b is 1/6 the size of vector b. It points in the same direction because it was a positive 1/6. So based on that information, I know that unit vector b points in the same direction as vector b. It's just 1/6 the size. So there you go. There's a unit vector that I constructed based on vector b. And that's a lot of what we're going to use these unit vectors for. You'll see them a lot more when you define coordinate systems. Well, you'll get used to some very familiar unit vectors. You'll use them over and over and over again. They're references that we're going to use to construct all of our other vectors from.